Flip a light switch. Light travels from the bulb to your eye at 300 million meters per second, except it doesn't travel. Not from the photon's perspective. If it had a perspective. You see, special relativity says something very strange about time. Something that makes perfect sense mathematically but sounds completely crazy when you first hear it. As you move faster, time slows down. Not for you, in your own reference frame. You feel perfectly normal, but relative to someone standing still, your clock ticks slower. This isn't philosophy, this is measurable. We've done the experiments. Take a very accurate atomic clock. Put it on an airplane. Fly it around the world. Compare it to an identical clock that stayed on the ground. The airplane clock is behind. By nanoseconds, but measurably behind. It experienced less time because it was moving. Joseph Haefel and Richard Keating did this experiment in 1971. They flew atomic clocks around the world on commercial airlines, eastward and westward. When they brought the clocks back, they compared them to reference clocks that stayed at the Naval Observatory. The flying clocks had lost time. Different amounts depending on which direction they flew, because the Earth's rotation matters too. But it matched the predictions of relativity exactly. We do this every day with GPS satellites. They're moving fast, orbiting Earth at about 14,000 kilometers per hour. Their clocks tick at a different rate than clocks on the ground. We have to correct for this, or GPS wouldn't work. Your phone wouldn't know where you are. Actually, there are two effects. The satellites are moving, so time dilation makes their clocks run slower. But they're also higher up in Earth's gravitational field, and general relativity says clocks run faster in weaker gravity. The two effects partially cancel, but not completely. The satellites gain about 45 microseconds per day from gravitational time dilation and lose about 7 microseconds from velocity time dilation. Net gain, 38 microseconds per day. That doesn't sound like much, but light travels 30 centimeters in a nanosecond. 38 microseconds is 11 kilometers of error per day. Without corrections, GPS would be useless within minutes. So time dilation is real, tested, verified, every single day. Now, the amount of time dilation depends on your speed. There's a formula. It involves the Lorentz factor, gamma. As your speed approaches the speed of light, gamma gets bigger and bigger. At 90%, the speed of light, time runs at about half speed. At 99%, it's about 1/7. At 99.9%, it's even slower. And at exactly the speed of light, the formula divides by zero. Time dilation becomes infinite. What does that mean? It means the photon's clock doesn't tick. Not slowly. Not at all. From the photon's perspective, if it had one, no time passes. Ever. Now, you probably heard of the twin paradox. One twin stays on Earth. The other twin gets in a rocket, flies away at high speed, comes back. When they reunite, the traveling twin is younger. Less time passed for them. This is real. Not a paradox at all, actually. Just relativity, working exactly as the mathematics predicts. Let me give you concrete numbers. Suppose the traveling twin goes to Alpha Centauri, about 4 light years away. They travel at 99.5% the speed of light. From Earth's perspective, the round trip takes about 8 years. The traveling twin comes back, and Earth's twin has aged 8 years. But the traveling twin, they experience time dilation. At that speed, their clock ran about 10 times slower. So for them, the trip took less than a year, maybe 9 months. They come back having aged 9 months while their twin aged 8 years. This isn't science fiction. This is what the equations predict. And every experiment we've done confirms it. But imagine you push this to the limit. What if the traveling twin could travel at the speed of light? Well, they can't. Nothing with mass can reach light speed. It would take infinite energy. The energy required to accelerate something with mass goes up as you approach light speed. At 90% C, it's already much more than the kinetic energy you'd calculate with Newtonian physics. At 99% C, it's enormous. At 99.99% C, it's absurd. At exactly C, it's infinite. You'd need infinite energy to accelerate even a single electron to light speed. That's why only massless particles can move at light speed. Photons have no mass, neither do gluons. They move at C, and only at c. They can't move slower, but pretend, just as a thought experiment. From the perspective of the twin traveling at light speed, no time passes. They leave, they arrive, it's the same instant. Their whole journey, even if it takes years from Earth's perspective, takes zero time for them. Every photon that hits your eye experienced this. From the sun, from a distant star, from the lamp across the room, all of them. Think about that. The photon leaves the sun. From our perspective, it travels for 8 minutes. 93 million miles. We can measure this. We know how long it takes. We can actually measure it. Ole Römer did it in 1676 by observing the moons of Jupiter. He noticed that the timing of eclipses changed depending on whether Earth was moving toward Jupiter or away from it. The difference was because light took time to cross Earth's orbit. That was the first measurement showing light has a finite speed. Not infinite, finite. But from the photon's perspective, zero time. It was emitted by a fusion reaction in the sun's core and absorbed by a molecule in your retina in the same instant. Not very quickly, not so fast it seems instant. Actually, literally, zero time. Now, you might say, well, maybe time just runs very, very slowly for the photon. So slowly we can't measure it, but it's not actually zero. No, the mathematics is clear. It's not approaching zero. It is zero, exactly zero. And it gets stranger. Length contracts too in special relativity. As you move faster, distances in your direction of motion get shorter. At 90% light speed, a meter stick looks about half a meter long if you're carrying it. At 99%, even shorter. At exactly light speed, the contraction becomes infinite. The distance contracts to zero. So from the photon's perspective, not only does the journey take zero time, but the distance is also zero. The sun and your eye are in the same place from the photon's point of view. Every photon from the farthest galaxy, 13 billion light years away, experienced zero distance and zero time. Born at a star. Died in your telescope. Same instant, same place. There's actually a beautiful symmetry here. Time dilation and length contraction are related. They're two sides of the same coin. If you're moving at some speed v, your time dilates by a factor gamma, and distances contract by the same factor gamma. At light speed, both go to infinity. Infinite time dilation means zero proper time. Infinite length contraction means zero proper distance. The photon's journey through space and time collapses to a single point event. Now, this sounds like I'm telling you the photon experiences some kind of strange, timeless, spaceless existence. Some mystical state. But I'd be cheating you if I left it there, because the photon doesn't experience anything. Experience requires time, a before and an after. The photon has no time. No before, no after. The question, what is it like to be a photon, doesn't make sense. Not because we don't know the answer, because the question itself is malformed. It's like asking, what's north of the North Pole? There's no answer because the question assumes something that isn't true. There's no north once you're at the North Pole. The concept breaks down. Same here. There's no reference frame moving at light speed. Not because we haven't found it, because it can't exist. The mathematics doesn't allow it. When you try to transform into the photon's reference frame, you divide by zero. The equations blow up. Infinity appears. That's mathematics telling you, stop, you've gone too far, this doesn't make sense. Let me tell you why this happens. It's in the structure of special relativity. Einstein's insight was that the speed of light is the same in all reference frames. If you're standing still and you measure light, it goes at c, 300 million meters per second. If you're moving and you measure light, it still goes at c, same speed, always. That's bizarre, right? Normally speeds add. If you're on a train moving at 50 miles per hour and you throw a ball forward at 20 miles per hour, someone on the ground sees the ball moving at 70. But light doesn't work that way. If you're on a train moving at half the speed of light and you shine a flashlight forward, someone on the ground doesn't see the light moving at 1.5 times light speed. They see it moving at exactly light speed. How is that possible? How do you move forward at half light speed, shine light forward at light speed, and have it still be light speed in another frame? The answer is that time and space have to adjust. Time slows down. Space contracts. The adjustments conspire perfectly so that light always goes at c. And here's the thing. This isn't just true for light. It's true for causality, for cause and effect. Nothing can travel faster than c. Not matter, not energy, not information. Because if something could, you could send signals backward in time. You could violate causality. Imagine you send a signal faster than light to a distant star. From your perspective, the signal arrives in the future. But from another reference frame, moving relative to you, that signal could arrive before it was sent. You'd have effects preceding causes, paradoxes, contradictions. The universe doesn't allow this. The speed limit isn't arbitrary. It's fundamental to the structure of spacetime. And light happens to move at that speed, not because light is special, because light has no mass. And massless things must move at c. But that only works for observers moving slower than light. If you try to be the light, if you try to move at exactly c, there's no adjustment that works. The math breaks. So you can't ask, what does the photon see? Because seeing requires a reference frame, and there is no reference frame for the photon. We say light travels because we experience time. We're massive observers. We sit here and watch the photon cross the room. Takes a few nanoseconds. We can measure it. But that's our story, our reference frame, our time. For the light, nothing. No journey, no experience, no time. You know, when I was learning this, I kept trying to imagine it. What would it be like to be a photon? And my professor said, you can't. You're asking a question that doesn't have an answer. I didn't like that. I thought he was being lazy. There must be some way to think about it. But he was right. The universe doesn't care if we can imagine it or not. The mathematics is what it is. And the mathematics says there's no valid reference frame at light speed. Period. Now, there's another way to think about this that might help, or might make it worse. In relativity, we talk about space-time intervals, the distance between two events in space-time. For massive particles, there's a proper time. The time measured by a clock traveling with the particle. That proper time is what the particle experiences. But for a photon, the space-time interval between emission and absorption is zero, null interval, the proper time is zero. It's not that we don't know the proper time. It's not that we can't measure it. It's that it is mathematically exactly zero. The photon traces out what we call a null geodesic, a path through space-time where the interval is zero. From the photon's, well, I can't say perspective, because it doesn't have one. From the space-time geometry's point of view, the emission and absorption events are connected by a zero interval. Let me give you another example. It's going to sound strange. Imagine you draw a straight line on a piece of paper, the shortest distance between 2 points. Now imagine you could be an ant walking along that line. The ant experiences distance, 1 millimeter, 2 millimeters, and so on. But now imagine the line itself. Does the line experience its own length? No. That's a nonsense question. The line doesn't experience anything. It's just a geometric object. The photon is like the line. It's a path through space-time. We, the observers, see the path. We measure its length in space and time, but the path itself doesn't experience anything. That's not a perfect analogy. No analogy is perfect here, but maybe it helps you see why the question doesn't make sense. Here's something else that bothers people. If the photon doesn't experience time, how does it know to keep moving? How does it go from the sun to your eye? But that's the wrong question too. The photon doesn't know anything. It doesn't decide to move. It just follows the laws of physics. Maxwell's equations describe how electromagnetic fields propagate. Light is an electromagnetic wave, or a photon in the quantum picture. It does what the equations say it does. And from our perspective, it moves at c, always, in all directions. But the photon doesn't have intentions. It doesn't have knowledge. It just is. We're so used to thinking about things from a conscious perspective. What do I see? What do I feel? What's it like? But most of the universe isn't conscious. Most of the universe just follows rules, equations, laws of physics. The photon follows the rules. The rules say it propagates at c. From our perspective, that looks like motion. From the photon's perspective, there is no perspective. Here's another weird consequence. Events that are simultaneous for one observer aren't simultaneous for another. If you and I are standing still relative to each other, and two things happen at the same time far apart in space, we agree they happen simultaneously. But if you're moving relative to me, you might see one event happen before the other. The order can change depending on your motion. This is called the relativity of simultaneity. Einstein called it the most difficult concept in special relativity. But there's a limit. Events connected by light can't have their order reversed. If a photon leaves event A and arrives at event B, all observers agree that A happened before B. That's because the photon travels on a null geodesic. The interval is zero, but the causal connection is preserved. The photon connects events in a way that's universal. All observers agree on the connection, even if they disagree on the time and distance involved. Now, let me tell you something even stranger. Every photon from the Big Bang, from the cosmic microwave background radiation, has been traveling for 14 billion years. 14 billion years from our perspective. From the photon's perspective, it was emitted at the Big Bang and absorbed by your radio telescope in the same instant. That entire 14 billion year journey took zero time for the photon. Think about what that means for the photon, if it could think, which it can't. The universe began, the universe ended. Same moment. No in-between. All of cosmic history, from the photon's point of view, is a single instant. The alpha and omega, beginning and end, collapsed into one. Of course, that's not how we experience it. We're massive. We have time. We watch the universe evolve. But the photons, they connect events across billions of years and billions of light years, as if those events were right next to each other. Time and distance are properties of massive observers like us, not of light itself. Let me be careful here. I'm not saying photons don't exist. I'm not saying light is an illusion. Light is real. It carries energy. It has momentum. You can feel sunlight warming your skin. That's real energy deposited by real photons. The energy of a photon is related to its frequency. E equals h times nu, Planck's constant times frequency. Higher frequency, more energy. Blue photons have more energy than red photons. X-rays have even more. Gamma rays from radioactive decay or cosmic events, those have tremendous energy. But the photon's subjective experience, if you want to call it that, is not defined, can't be defined. The mathematics doesn't allow it. It's like asking what color a sound is. The question assumes something that doesn't apply. Sounds don't have color. Photons don't have reference frames. You know, there's a particle that gives us a beautiful demonstration of time dilation. The muon. Muons are created high in the atmosphere when cosmic rays hit air molecules. They're unstable. They decay in about 2 microseconds, on average. Now, these muons are moving very fast, close to the speed of light. From our perspective on the ground, they're created maybe 15 kilometers up. But if they only live 2 microseconds, and even at near light speed they can only travel about 600 meters before decaying, how do they reach the ground? They shouldn't. Almost none of them should make it. But we detect them. Lots of them. They reach the ground all the time. Why? Time dilation. From our perspective, the muon's clock is running slow. So it lives longer than 2 microseconds. Long enough to reach the ground. From the muon's perspective, it only lives 2 microseconds. But the distance is contracted. The 15 kilometers of atmosphere is compressed to maybe 600 meters. So it has enough time to get through. 2 perspectives, both correct, both explaining the same observation. That's relativity. Different observers, different measurements, but consistent physics. If the muon were moving at exactly light speed, it would experience 0 time and 0 distance, like a photon. But muons have mass, so they can't reach light speed. You know, physics is full of these situations where common sense fails, where intuition breaks down. We evolved to understand medium-sized objects moving at medium speeds, rocks, animals, other people. We didn't evolve to understand things moving at light speed, or things at the quantum scale, or things near black holes. So our intuitions fail, and that's okay. That's what the mathematics is for, to guide us where intuition can't go. The mathematics of special relativity is crystal clear. tested extensively, predicts everything correctly. And it says, no reference frame at light speed, no proper time for a photon, no experience. That's just how it is. Strange, isn't it, that the fastest thing in the universe, the thing that connects all events, the thing that lets you see the stars, doesn't experience motion at all. From our perspective, light is the ultimate traveler, racing across the cosmos, the speed limit of the universe. From the light's perspective, it never moves. It never experiences anything. Born and gone in an instant. Two completely different stories. Both true, both valid in their own reference frames. That's relativity. Different observers see different things. But the laws of physics work the same for everyone, and if you're light itself, there's no you to see anything at all. That's roughly where we are. We can describe what happens, we can write the equations, we can make predictions that match experiments perfectly, but we can't imagine what it's like to be a photon, because there's no what it's like. The question itself assumes time, and the photon has no time. Maybe that's the deepest lesson of relativity. The universe doesn't have to make sense to your intuition. It doesn't have to feel comfortable. It doesn't have to be something you can picture. It just has to be consistent. And it is beautifully, perfectly consistent. The photon is born, the photon dies, same instant, no journey in between. And yet, from our perspective, it traveled. It carried information. It brought light from the sun to your eye. Two truths, one reality, different reference frames. Interesting.